let's talk about what the FAA wants commercial pilots to know about aerodynamics. And this is a magnificent example of aerodynamics. Look at that thing fly. Well, the FAA wants you to know what makes an airplane fly and what makes an airplane stall, and when the airplane's going to fly and when it's going to stall. And I don't believe this thing really flies. I've been told it's a mass hallucination. I think it's not aerodynamics at all. Well, it really is. So let's talk about the aerodynamics and what you need to know about it. And let's lead off by talking about Bernoulli's law. Now, I used to say this guy that studied air going through a tube was an Italian guy because the name's Bernoulli, but somebody of Swiss descent told me, John, that's not right. He's a Swiss guy. So there's a Swiss guy that used to study how air goes through a tube. And he learned some things very interesting. It's what makes an airplane fly, is what he learned. And what he learned is if you measure the air pressure as the air goes through the tube, when the air gets to the narrow part, it has to go faster to get through that tube. And at points where the air is going faster through this tube, the pressure is the least. So the points where the air is going the fastest, the pressure is the least. And you might look at this, and it looks like we have two wings here, and we do. So let's take one wing away, and you have the same effect. You have a wing, and air is forced to go over the top of the wing, and that air speeds up. Now you might say, wait a minute, why doesn't that just compress instead of speeding up? Well, the fact is that free air will not compress. If you could trap it in a gallon jug, you can compress air, but free air won't compress, it just moves out of the way. So this air that gets forced to go over the top of the wing moves faster, and Bernoulli's law says that there is therefore lower pressure at the top of the wing. And you can measure it with a gauge, measure it any way you want, and there is low pressure on top of the wing, relative high pressure underneath the wing, and that's the pressure differential that creates lift. Now the FAA wants you to know that an aircraft wing is designed to produce lift resulting from, and I'm giving you magic words from the FAA written exam, relative positive air pressure underneath the wing or below the wing surface and negative air pressure over the top of the wing surface, and that's what creates lift, and that's Bernoulli's principle. Now, let's get a couple other terms out of the way, and one of these terms we want to talk about is angle of attack. And let's start off by drawing a line from the trailing edge of the wing to the leading edge of the wing. If you draw a line from the trailing edge of the wing to the leading edge of the wing, that line is a chord line, and it roughly points the direction the wing is pointed, like so. Now, if the airplane wing is going this direction, the relative wind will be coming from the opposite direction. And that angle between the chord line of the wing and the relative wind, that angle is called the angle of attack. And the FAA wants you to know the angle of attack of the wing directly controls the distribution of the positive and negative pressure acting on the wing. And when you increase the angle of attack, you increase lift and you also increase drag. So by changing the angle of attack of a wing, you can, as a pilot, control the airplane's lift, airspeed, and drag. And as you increase this angle of attack, the lift gets greater, you have lower pressure on top of the wing, and higher pressure underneath the wing, and more lift, but at the same time, you have more and more drag as you increase the angle of attack of the wing. So it's by controlling of the angle of attack, you can control lift, airspeed, and drag. Now, an increase in angle of attack will increase impact pressure below the wing, and it will also, as a result, increase drag. Now, let's assume you're flying along in what the FAA calls steady, unaccelerated flight. That means you're not speeding up or slowing down. You're in steady flight. And the FAA wants you to know in steady, unaccelerated flight, there is a corresponding indicated airspeed required for every angle of attack to generate sufficient lift to maintain altitude. So the slower you go, the more angle of attack you have to have. The faster you go, the less angle of attack. But for every angle of attack, there's a corresponding speed to maintain the same altitude. Or you could put it the other way around. For every angle of attack, there's a speed. For every speed, there's an angle of attack also. Now, to maintain altitude while your airspeed is being decreased, what would you have to do then? Increase or decrease the angle of attack. Well, if you slow this airplane down, you want to maintain altitude, you're going to have to increase the angle of attack to generate more lift. They call that coefficient of lift, increase the lift, for a given speed. So as you slow the airplane down, you have to increase the angle of attack to compensate for the decreasing lift. Now, let's assume you want to transition from straight and level flight to a climb. What do? Well, you momentarily increase the angle of attack, and lift will be momentarily increased at the same time as you increase that angle of attack. Now, as altitude gets higher, the air gets thinner. Now, that thin air affects your pitot tube in exactly the same way it affects the wings. So the airplane will stall and fly at the same indicated airspeed at high altitude as it would at low altitude. But what is your true airspeed over the ground going to be when you're in thinner air? And the answer is you're going to actually be going at faster true airspeed for a given particular angle of attack. So to generate the same amount of lift as altitude is increased, and I'm giving you the answers for an exact FAA written exam question, an airplane must be flown at a higher true airspeed for any given angle of attack as you go to higher altitude. And that's because to get the same indicated airspeed, you have a higher true airspeed. Now, when an airplane is flying, the air is flowing smoothly over the surface of the wing and conforming to the surface of the wing. And that's, of course, what creates lift. And as you increase the angle of attack, then you have more lift and you have more drag. And you keep increasing the angle of attack, you can get more and more lift until finally you increase the angle of attack to the point where the air can no longer conform to the surface of the wing. And it'll begin to backfill and burble and eddy. And where that is happening, lift is destroyed. And as you increase the angle of attack further, more and more of the wing begins to stall, and lift will be destroyed. And finally, when you reach a critical angle of attack, nearly the entire wing has lost its lift, and that's called the critical angle of attack. And it has to do with the relationship between the chord line of the wing and the relative wind. And that causes the air to flow backwards and backfill and burble like that. Now, the FAA is going to ask you, when does an airplane stall? And the answer is an airplane stalls when you reach the critical angle of attack. And the question is, does the critical angle of attack change? And the answer is no. For any given wing shape, the critical angle of attack remains constant regardless of anything else that's going on. So no matter what they put in this list, the critical angle of attack remains constant because an airplane stalls at a specific angle of attack. So it remains constant regardless of weight, dynamic pressure, that's the air forcing itself over the wing, bank angle, pitch attitude, attitude with relation to the horizon. They could put anything in this list, and the answer is the angle of attack at which an airplane's wing stalls remains constant regardless of anything you might put in that list because an airplane stalls at the same critical angle of attack at all times. So you can see that this angle of attack, especially the critical angle of attack for a particular wing, rules everything. And then the airplane stalls at a specific critical angle of attack. Now let me ask you a question. If you have an airplane, we'll say, illegally over gross weight, would that airplane stall at a higher indicated airspeed or lower indicated airspeed? And the answer is it would stall at a higher indicated airspeed because it'll get that critical angle of attack at a higher speed because the airplane is heavy. So let me ask you another question. Is the stalling speed of an airplane a fixed value? And the answer is no. You'll get that angle of attack at different speeds depending on the weight of the aircraft. So the indicated stalling speed of the airplane is affected by such things as the weight of the aircraft, the load factor, that means the G's you put on the aircraft. You pull out of a dive, everything in the airplane feels like it weighs twice as much, and power, because when you have power off, there's less air over the wings. When you have power on, there's more air over the wings. So those three things will affect the indicated stalling speed of an airplane. So the stalling speed of an airplane is not a fixed value. The stalling angle of attack is a fixed value, and you'll get that angle of attack at different speeds depending on weight, load factor, and power. Now, how about turbulence? If you get in a lot of turbulence, can that cause the aircraft to stall at a different speed? And the answer is, yeah, turbulence can cause an increase in stall speed. Matter of fact, they're going to ask you two things that turbulence can do for you. One of the things that turbulence can do is cause an increase in stall speed. The other thing turbulence does to you, and it's a completely separate question, is that it requires you to slow an aircraft below maneuvering speed in turbulent weather. So what happens is, because when you get in turbulence, you should slow the airplane down to protect the airplane. You should slow it down below maneuvering speed. That's VA. We'll talk more about that later. And you also have an increase in stall speed that so you can see your safe envelope kind of narrows on you. Your stall speed increases, and you need to slow the airplane down to protect the airplane. So in turbulence, your safe envelope kind of narrows down on you. Now, let's assume that you go out to the airport someday and you notice a little bit of frost on the wings of the aircraft. For instance, here's a case where there might be just a little bit of frost on the wings of the aircraft, and you might notice it. Let's hope you would notice it. Well, anything that interferes with the smooth flow of air over the upper surface of the wing can change the way an airplane flies and could cause it to stall at a higher speed and at a lower angle of attack. So the trick is, if you get out to the airplane and there's even a little tiny bit of frost, you need to take some plastic, preferably not your favorite credit card, and scrape off every bit of ice. So frost covering the upper surface of a wing will cause an airplane to stall at an angle of attack that is lower than normal. Obviously, it does not have to be this extreme. You can have a very small amount of frost, and it can be a problem for you. Now, the plan form, the FAA calls it, that is, the shape of a wing as compared to other shapes of wings, can change the way an airplane stalls. This is a rectangular wing, and when you notice when this airplane stalled, it stalls near the root first, and the stall progresses out to the wingtip. We saw that earlier when this airplane stalled. So what that does for you is gives you better control of the airplane throughout the stall because, of course, the ailerons are near the wingtip and you have better control. So a rectangular wing, as compared to other wing plan forms, has a tendency to stall first at the wing root. We saw that happen with the stall progressing towards the wingtip. Now, when you're approaching to land at an airport, it is customary to use flaps. Now, one of the questions they're going to ask you on the test is, why would you use these flaps when you're approaching to land at an airport? And the answer is, one of the main functions of flaps during approach to land at an airport is to provide the same amount of lift at a slower airspeed. So flaps let you fly slower on approach. And of course, when the flaps are extended, you increase lift. That's why you can fly slower, but you also increase drag. So when flaps are extended, both lift and drag are increased. Now, what happens when you raise the flaps? When you raise the flaps, you increase the stalling speed because you have a little less lift. So they're going to say, let's assume you're in a turn at level altitude and you raise the flaps. What's going to happen? Well, you're going to increase the stall speed of the aircraft. So the moral to that story is just be careful when you raise the flaps. In some cases, you might have needed those flaps because you do increase your stalling speed. Let's take a look at some forces on the aircraft. And one of the forces we need to talk about is lift. And they're going to ask you, how would you define lift? And you can think of a whole bunch of guys sitting around the room and say, hey, I got it. Let's call lift that force produced perpendicular to the relative wind. Here's the relative wind, 90-degree angle, that's lift. You can see it's arbitrary as to how you define lift. The convention is that lift is that force produced perpendicular to the relative wind. Drag, on the other hand, is that force produced parallel to the relative wind and in the same direction. So you can see here is drag parallel to the relative wind, and here is lift perpendicular to the relative wind. Lift also acts perpendicular to the flight path of the aircraft because that's where the relative wind is coming from, opposite the flight path of the aircraft. Well, once again, the force of drag acts parallel to the flight path because the relative wind comes opposite the flight path. Now, let's assume that you're flying along in steady state flight. What are the forces on the aircraft then? Well, they want you to know that you have to have some force to propel the airplane along, and that's generally created by the propeller, and that is called thrust. Another force that slows the airplane down over here is called drag. You can think of it as a ball and chain, apparently. And then you have the weight of the aircraft, and that is enormously heavy, and then you have lift. Well, if an airplane is flying along in a straight line at a constant speed, thrust is equal to drag, because if thrust were not equal to drag, the airplane would be changing speed or direction. And lift is equal to weight, because if lift were not equal to weight, the airplane would be changing speed or changing direction. So any time an airplane is in a straight line at a constant speed, the sum of all rearward forces is equal to the sum of all forward forces. Because if they were not equal to each other, the airplane would be changing speed or changing direction. So in steady state flight, the opposing forces, the lift and the drag and the thrust and the drag, or the lift and the weight and the thrust and the drag, are all equal to each other. But now let's assume you put this airplane into a little descent. During the time that you're changing speed and changing direction, those forces are no longer in balance. But once you have established that airplane in a steady state descent in a straight line at a constant speed, once again, thrust is equal to drag and lift is equal to weight. Because if they were not equal to each other, the airplane would be changing speed or changing directions. So even in a steady state descent, the sum of all rearward forces is equal to the sum of all forward forces. Now, let's talk about some other things the FAA wants you to know about. And the biggest thing you need to know about is more about drag. And here's a chart that talks all about drag. Across the bottom is the velocity of the aircraft, how fast you're going through the air. On the left-hand side is the drag on the aircraft in pounds. And there are basically two kinds of drag. One is parasite drag. It's the drag of the skin friction and forcing of the air out of the way. And parasite drag increases as the speed of the aircraft increases. In fact, parasite drag increases with the square of the speed of the aircraft. So as you go faster and faster, parasite drag becomes very, very important. Now, the other kind of drag we need to talk about is called induced drag, and that's the drag caused by the angle of attack when you're producing lift. And the more angle of attack you have, the more induced drag you have. So that means the slower the airplane goes, the more induced drag you have because the angle of attack is greater. And it's a byproduct of producing lift. And as you get slower and slower, you have more and more angle of attack and more induced drag. So induced drag decreases as speed increases, and parasite drag increases as speed increases. Now, if you add those two together, you get total drag. And total drag has a shape like this as far as speed is concerned, and here's the way it works. As you are going slow and you're near stall speed of the aircraft, induced drag is very high, and parasite drag is very small. As you increase the speed of the aircraft, parasite drag becomes more, but induced drag becomes less at a faster rate, until finally, at a certain magic speed or angle of attack of the aircraft, you have minimum drag right there. And that's the point where you have the least drag and a maximum ratio of lift over drag. Lift is the same. You're keeping the airplane in steady state flight here. You're not losing altitude anyway. Let's put it that way. You're not losing altitude. So lift is the same. So at the point where the drag is the least on this drag velocity curve, you're going to find that you have maximum ratio of lift over drag, and it's this point right here. So your induced drag goes down as the speed increases, but parasite drag goes up, and as you get to a certain point where you get faster and faster, now you're over here where you're to the point where parasite drag becomes much, much more. Now, you've heard of people saying, well, he's on the back side of the power required curve. Well, here's what we're talking about. As an airplane gets slower and slower, it takes more and more thrust to keep the airplane flying. And when you're in the point where it takes more and more power to fly slower and slower, they say you're in the region of reverse command, or it's commonly thought he's flying on the back side of the power required curve. And I've had my whole life go like that, where I'm just dragging myself along. In fact, in an airplane, we'll say it stalls at 50, full power stall speed, you're going to be at full power, and you're doing all you can to maintain altitude at full power, and that's what you call the region of reverse command. You're on the back side of the power required curve. Okay, so if you want to have maximum range and maximum distance glide, you'd find that at max L over D, the lowest point on the power required curve here, and that's in a propeller-driven airplane. Now, as the airspeed decreases below that speed for maximum L over D in level flight, the total drag of an airplane increases because of which kind of drag? And the answer is induced drag. So induced drag is a byproduct of lift and is greatly affected by changes in airspeed. That is induced drag, and that's this one right here. As you get slower and slower, you get more induced drag. Now, if the angle of attack and other factors remain constant and the airspeed is doubled, what happens is parasite drag increases by 4 times. It'd be 4 times great because parasite drag increases by 4 times, or squares, increases with the square of the speed. So if you double your speed, parasite drag will be 4 times greater. Also, lift acts the same way. Lift will be 4 times as much also as you double your speed because it also works with the square of the speed of the aircraft. Now, let's take a good, close look at Figure 1. And the reason I want to do that is I want to point out points A and B because this is going to be the answer to a question on the test. And the question is, what is the significance of the airspeed represented by points A and B in steady flight? And the answer is, in steady flight, an airplane will have its maximum lift over drag ratio at each of those points and maximum glide range at that airspeed right there. That's maximum L over D. Now let's you and I take a look at Figure 3, and we'll talk some more about L over D, or lift over drag ratio. Across the bottom of Figure 3, you see angle of attack. So as you go to the right, angle of attack increases. And on the left-hand side of Figure 3, it says coefficient of drag, so that's a scale that tells you how much drag you have for a given angle of attack. And on the right-hand side, Figure 3, it says coefficient of lift. That's a scale that tells you how much lift you have for a given angle of attack. And on the far right side, there's a scale for lift over drag ratio. And here's a scale for that. Now, let's take a look at this chart and see if you and I can make some sense out of it. First of all, as the angle of attack increases, you have here a curve that tells you what's going to happen to the lift over drag ratio. And it starts out As the angle of attack is 0, lift over drag ratio is 0, and as the angle of attack increases, the lift over drag ratio increases, meaning you have more lift with less drag, until finally you get L over D max. Let's stop right there and talk about max L over D for a second. That is we talked about it earlier, it's the point where your drag is at the minimum, and notice that you get max L over D at a specific angle of attack. And that's a very important thing, because max L over D is where you have maximum range airspeed. And what they want you to know is you get that maximum range airspeed at a specific angle of attack. And as the weight decreases, you decrease the speed for maximum range airspeed, because maximum range occurs at a specific angle of attack. So when you have less weight on the aircraft, you'll get that specific angle of attack at a lower weight or lower speed, and when you have more weight on the aircraft, you'll get the specific angle of attack at a greater speed. So maximum range airspeed actually decreases when weight decreases, because it occurs at a specific angle of attack. Now let's you and I take a look in the lower left-hand corner here of figure 3, and let's take a look at 2 degrees angle of attack here, and let's read up from 2 degrees angle of attack until you hit the L over D line. Now the question they're going to ask you is, the L over D at 2 degrees angle of attack is equal to the same L over D as what other angle of attack? And you'll go across and read it parallel from the 2 degree angle of attack where it hits the L over D line, and read right straight down again when you hit the L over D line again, and you find out that the 2 degree angle of attack is equal to the same L over D as you'd get at 16.5 degrees angle of attack. What's the purpose of that? I don't know. They just want to know if you can read this particular chart. Now, another thing you need to know is there's a lot of other curves on here. What do they have to do with? Well, here's a line that tells you what the coefficient of drag is for a given angle of attack, and the coefficient of drag will increase as the angle of attack increases. Another line here will tell you what happens to lift as you increase the angle of attack. So here's the coefficient of lift, and of course that's the stalling coefficient of lift up here. When you get to the particular angle of attack where it stalls, and it begins to drop off very rapidly. So that's what the other lines are. The only line they ask you about, however, is the L over D line. For instance, they're going to say if an airplane glides at an angle of attack of 10 degrees, how much altitude would it lose in a mile? Well, let's look at the 10 degree angle of attack here, and there's the 10 degrees. You go up to the 10 degree angle of attack, go up to the L over D, and read all the way across the far right-hand side and see what the lift over drag ratio is, and you see the lift over drag ratio would be about 11. So the question is, at a 10 degree angle of attack, how much altitude would it lose in a mile? Well, if the lift over drag ratio is 11, that tells you the airplane will go 11 feet forward for each foot that it goes down. So now let's find out how much altitude it will lose in a mile over the ground. All right, the lift over drag ratio was 11, so it's 5,280 feet divided by the lift over drag ratio. 5,280 feet divided by 11, that means that the airplane will go a mile forward while it only loses 480 feet, and that's what the L over D, lift over drag ratio of 11, means. And so it would lose 480 feet in 1 mile forward. Let's do another one. They're going to say how much altitude will this airplane lose in 3 miles of gliding at an angle of attack of 8 degrees. Well, let's find out what the L over D is at 8 degrees. So you go down here at 8 degrees, you go up until you hit the L over D line, stop and make a dot, then read over in the far right-hand side, and at 8 degrees you find out the lift over drag ratio happens to be about 12. Well, it's 12 exactly according to this chart. So let's figure out the formula and see how much altitude you're going to lose in this particular case in 3 miles of gliding. Well, the distance is 3 times 5,280 feet. The L over D is 12. Divide that by 12. In 3 miles of going forward, you will lose 1,320 feet. It's 3 times 5,280 feet per mile. You need to know, by the way, it's 5,280 feet per mile. So 3 times that divided by 12. And in gliding 3 miles forward, it'll only go down 1,320 feet. Okay, now let's take a look at an airplane and talk about one other type of force on the airplane. We've covered drag real well, but here's an airplane flying along. Isn't that a gorgeous shot of an airplane flying along? And notice the propeller is turning clockwise. And when this propeller turns clockwise, it tends to swirl the air clockwise around the aircraft like that. Now, as the air swirls around the airplane, you can see what happens is the air will hit the tail on the left-hand side. And that air hitting the tail on the left-hand side does two things. First of all, it makes the tail want to go to the right. In other words, it'll try yaw the whole airplane around like that. So the airplane will yaw about the vertical axis. The vertical axis is a line drawn from the floor to the ceiling of the aircraft right straight up. And so the airplane will yaw about the vertical axis, and the airplane will also tend to roll because the air hits the tail here. Now, nothing underneath the airplane gets hit. There is no tail sticking up underneath the airplane, so nothing underneath the airplane gets hit. So what happens, this air swirls around the airplane like so and hits that tail, as you can see, and it makes the airplane yaw to the left and roll to the right. So the FAA is going to say a propeller rotating clockwise, as seen from the air, will cause what to happen? Well, it creates a spiraling slipstream that tends to rotate the airplane to the left around the vertical axis and to the right around the longitudinal axis. The longitudinal axis is the line drawn from the nose of the aircraft to the tail of the aircraft. Let's take a look at these axes of an aircraft right here, and let's see if you and I can make some sense out of them. First of all, if you draw a line from the nose of the aircraft to the tail of the aircraft, that is called the longitudinal axis of the aircraft, and the aircraft rolls about that longitudinal axis. If you have a line going from, and that line, by the way, has to pass through the center of gravity of the aircraft. And if you have a line going from the floor of the aircraft to the ceiling of the aircraft, and that line passes through the center of the gravity, that is the vertical axis of the airplane, and the airplane yaws about the vertical axis. And if you have a line drawn from wingtip to wingtip, and it passes through the center of gravity, the airplane will pitch about that line, and that line is called the lateral axis. The airplane pitches about the lateral axis. Now, all of these axes intersect at the center of gravity, and all rotations of an aircraft take place around the center of gravity. Now, let's see what that means to us. Well, one of the things it means to us is how the airplane is going to behave in flight, and let's talk about various kinds of stability. And let's talk about what makes an airplane stable versus unstable in the air. First of all, when an airplane is flying along, you normally will have a slight aerodynamic downforce on the tail. In most general aviation airplanes, that always surprises people, but the tail's actually trying to fly down. And the reason there's an aerodynamic downforce in the tail, that downforce helps make the airplane stable as far as pitch and speed are concerned. Now let's talk about it. First of all, see where the center of lift is on this airplane. Now technically, they don't call that the center of lift, they call that the center of pressure. But we'll call it the center of lift for right now. But pick this airplane up by a string where the center of lift is. Notice where the center of gravity is. If you pick this airplane up by a string where the center of lift is, the center of gravity is in front of it, the airplane's going to want to pitch down. In order to keep from pitching down, there's an aerodynamic downforce in the tail, and that keeps that airplane from pitching down when it's flying. And the airplane is designed so that it's flown exactly that way, and here's why. Look what happens now if this airplane's nose gets down, the airplane picks up speed and starts going too fast. Now there's more air over the tail and more downforce on the tail, and with increased speed, the airplane's nose will come back up, the airplane will climb, lose speed, and return to its original speed. This aerodynamic downforce on the tail helps make the airplane stable as far as pitch and speed are concerned. You say, well, what if the airplane gets too slow? Well, if the airplane gets too slow, there's less air over the tail will come up, the airplane will dive, pick up speed, and return to its original speed. So that aerodynamic downforce on the tail helps make the airplane more stable as far as pitch and speed are concerned. And by the way, the further forward the center of gravity is, the more downforce there is on the tail, and therefore the more stable the airplane is. So you can change the stability of the aircraft by changing the loading of the aircraft, by changing the relationship to the center of gravity to the center of lift. Can you move the center of lift in an airplane? Not without a hacksaw. But can you move the center of gravity? Sure, just put bags or bricks in a baggage compartment back here. So you can move the center of gravity around, and you can change the stability of the aircraft by where you load the load inside the aircraft. Now, longitudinal stability is referred to as that kind of stability about the lateral axis. So longitudinal stability is motion about the lateral axis, that's pitching up and pitching down. That's called longitudinal stability. Now, there's two types of longitudinal stability, and they are static and dynamic longitudinal stability, and let's you and I illustrate how they work. First of all, we have static stability. If you press forward on the wheel and let go. Now, I don't know why anybody would want to do that, but if you press forward on the wheel and let go, and the nose will go down, and if the nose comes back towards equilibrium, the airplane has what is known as positive static stability. The nose returns to its original position after the elevator control is pressed forward and released. That's positive static stability if it does come back. Now, if you press forward on the wheel and let go and the nose just stays down, that would be neutral longitudinal static stability. The nose remains in the new position after the elevator control is pressed forward and released. And if the airplane gets worse and worse and worse, that would be negative static stability. Now, let's talk about dynamic stability. Dynamic stability, we all know, works like this. We all know that if you press on the wheel and let go, the nose just doesn't come back to equilibrium and stop. You have oscillations. And if the oscillations get smaller and smaller and smaller, you have positive dynamic stability. If, on the other hand, the oscillations get bigger and bigger and bigger, you have longitudinal dynamic instability. Now, longitudinal dynamic instability can be identified by pitch oscillations that become progressively steeper. It gets worse and worse and worse. Now, what did we say determines the stability of an aircraft? The center of gravity in relation to the center of lift or pressure determines the stability of an aircraft, as we said earlier. Now, what happens if you load an airplane to the rear of its aft CG limit, to the rear of its CG range? Will it be stable or unstable about its lateral axis? Well, if you move the CG far enough back, it's going to be unstable about its lateral axis. So where you load the load in the aircraft is the important thing for you to know about as a pilot. Now, let's assume you have the airplane loaded aft, real far aft, maybe even aft of the rear CG limit. Would stall recovery be easier or tougher? And the answer is stall recovery becomes progressively more difficult if the CG is located further aft. And if you get far enough aft, you'll have difficulty recovering from the stall because the airplane tends to fall tail first, and you can't get the nose down for recovery from the stall. Personally, I will never, ever load an airplane aft of its rear CG limit again. Oh, I tell you, terrible experience. Let's assume you do happen to stall the airplane. Let's assume you do it uncoordinated. Well, if that happens, this is what's going to happen to you. The airplane is going to spin, and it's going to scare the daylights out of you if it happens to you accidentally. Well, the FAA wants you to know just a little bit about spin, so let's take a look about what the FAA wants you to know. First of all, two things they want you to know. Recovery may become difficult or maybe even impossible if the CG is too far rearward. And all rotations in a spin take place around the center of gravity. Matter of fact, all rotations of an aircraft take place around the center of gravity. But in a spin in particular, that's important because the airplane rotates around the center of gravity and everything gets flung to the outside of the airplane. So let's assume you look at the turn and bank indicator and you're looking at that ball. What you're going to find is the ball will be off to one side. In fact, if the instrument is installed on the left-hand side of the aircraft, the ball will be to the left, generally slung all the way to the left-hand side. Now, they don't call this the ball on the FAA written exam. They call that the inclinometer. So if the inclinometer is on the left side of the panel, a spin to the left would displace the ball to the left. Spin to the right would also. It just depends on where it's mounted inside the aircraft. Now, let's take a look at an airplane and let you and I turn that airplane. The FAA is going to ask you what's going on inside an airplane, or as far as an airplane is concerned aerodynamically, when it's turning. Well, a lot's going on when the airplane's turning. Isn't that pretty? I like that a lot. A lot's going on when the airplane's turning. So let's have an airplane fly straight and level first, and then let's take a look at what happens to the airplane when it turns. When an airplane is flying straight and level, lift, which you can think of as being through the ceiling of the aircraft, is all vertical. And, of course, the wings have to support the weight of the aircraft, which is right straight down. Now, let's you and I bank this airplane for a turn. And when we bank the airplane for the turn, we tilt that lift. And that lift, which was vertical, is now out through an angle like this. And now there is both a vertical component of lift and a horizontal component of lift. And it's that horizontal component of lift that makes the airplane turn. At the same time, the wings not only have to support the weight of the aircraft, but they also have to support centrifugal force. So the whole airplane acts as if it weighs more, and that's called load factor. When the wings have to support more weight than the airplane actually weighs, that's called load factor, and centrifugal force is causing load factor on the aircraft at this particular time. Now, when you roll the airplane into a bank then, effectively, the airplane gets heavier, and that increases the stalling speed of the aircraft. So banking an airplane for a turn increases the stalling speed. How much? Let's take a look at figure 2 here, and you see we have an airplane here, power on, and let's take a look at the stalling speed knots. Let's start with the gear and flaps up. And you have this airplane in a 30-degree bank, power on, gear and flaps up. The stalling speed in level flight is 54, 30-degree bank, 58, 45-degree bank, 64. And finally, you roll this airplane into a 60-degree bank, you can see the stalling speed is increased up here to 76. So when you roll the airplane into a bank, it does increase the stalling speed of the airplane. Now, do power on stalls occur at lower airspeed in shallower banks or steeper banks? Well, lower airspeeds in shallower banks, higher airspeeds in steeper banks. Okay, now, how many knots higher will the airplane stall in a 60-degree bank with the gear and flaps up than with the gear and flaps down? Well, we already took a look at the gear and flaps up. In knots, the stalling speed, gear and flaps up, 60-degree bank is 76. Put the gear and flaps down in knots, the stalling speed is 66. So they're going to ask you this on the test, and all you have to do is look at figure 2 to figure it out, and the answer is 10 knots. So as the bank angle is increased in an airplane, the airplane gets effectively heavier, and there's more load factor on the aircraft. So let's take a look at all the things that happen as you increase this bank angle. First of all, the vertical component of lift would get less because you're tilting the lift unless you have back pressure on the wheel to increase the angle of attack, to increase the vertical component of lift. And the horizontal component of lift, of course, increases when you bank the airplane. So as you bank the airplane, you're tilting the lift, and unless you have back pressure, the vertical component of lift will get less, and of course the horizontal component of lift increases. So if you're banking an airplane for a turn, and you'd like to maintain altitude during that turn, what you have to do is increase the angle of attack with increased back pressure to compensate for the loss of the vertical component of lift when you bank the airplane for a turn. As you can see, there is a lot going on when an airplane turns. Now the FAA will go even further and ask you more questions about this. They're going to say, what determines the rate and radius of turn of an airplane? Well, there's two things that determine the rate and radius of turn. One is the angle of bank, and the other is the airspeed of the aircraft. In a coordinated turn at a constant altitude for a specific angle of bank and for a specific airspeed, you're going to get a specific rate and radius of turn. It will not vary. It will stay the same if you have a given bank angle and a given airspeed. But for any given bank angle, the faster the speed of the airplane, the greater the turn radius, and the slower the rate of turn. Now, you can help yourself think of that. Think of a car on ice, and it's a real icy parking lot here, and you're trying to turn around. Well, the faster that car is going, the slower the rate of turn, and the larger the radius of turn of that car. So let's assume you want to increase the rate of turn, and let's assume at the same time you'd like to decrease the radius of turn. What would be the best thing you could possibly do? Well, if you want to increase the rate and decrease the radius, you steepen the bank and decrease the airspeed. Both of those things will work in your favor. So increase the rate of turn and decrease the radius, steepen the bank, and decrease the airspeed. By the way, you could also maintain the bank and decrease the airspeed, and that would increase the rate of turn, but it's not as efficient as doing both of these things. Now, let's assume you want to maintain altitude as you increase the airspeed during a turn. Well, anytime you increase the airspeed of the airplane, and you're in a turn, for instance, you're going to have more lift on the wings. So if you want to maintain altitude while increasing the airspeed in a turn, what could you do? Now, what this question boils down to is if you're in a turn and you feel the airplane climbing, what would be a good way to keep the airplane from climbing? And the answer is steepen the angle of bank. If you steepen the angle of bank, you decrease the vertical component of lift. Conversely, if you're in a turn and you feel yourself losing altitude, one of the things you could do is roll out of the bank. So the answer on the FAA written exam is to maintain altitude. If your airspeed is increased during a level turn, what you must do is increase the angle of bank, or you would have to decrease the angle of attack. You could ease off on the back pressure on the wheel. Now let's talk about load factor on an airplane. The load factor occurs when you roll an airplane into a steep bank, put a lot of G's on it, or pull out of a dive. That'll put a little load factor on an airplane, or fly in turbulence. So if an airplane, for instance, flies along, the airplane really weighs 2,000 pounds, but it feels like it weighs 4,000 pounds, the airplane would have a load factor on it. So load factor is the total air load imposed on the wings divided by the total weight of the aircraft, and load factor directly affects the stalling speed of the aircraft. It is as if that airplane got heavier all of a sudden. To find out how much heavier that airplane gets when you roll it into a steep bank, let's you and I take a look at Figure 4. Now, across the bottom of Figure 4 is the bank angle. It goes 0, 10, 20, 30, 40, 50, 60 degrees all across the bottom here. And on the left-hand side is the percent increase in stall speed. And the far left-hand side is the load factor. That's the number of G's you're putting on the airplane. Now, if you look at this chart, you'll notice there are two lines here. This line is for stall speed increase, and this line is load factor. So if you start down at the bottom at a 60-degree bank and go up to the second line, that's your stall speed increase, and find out where that line hits the 60-degree bank, read across, you'd find your percent increase in stall speed is about 40%. And that same 60-degree bank, you go up to the first line, which is the load factor line, read all the way across to the left, and you'd find out you have 2 G's on the airplane. So the FAA is going to ask you a question about this. They're going to say, let's assume that you have a 2,000-pound airplane, and you roll that airplane into a constant altitude 60-degree bank. First of all, what's the load factor on the airplane? And the answer is that you would have a load factor of 2. So if the airplane originally weighed 2,000 pounds and you have a load factor of 2, to find the total load, you take the load factor times the weight, and the total load the wings of that airplane would have to support would be 4,000 pounds. So you can see that there is wing loading on an airplane when you roll the airplane in even a level coordinated turn in smooth air. And the amount of wing loading depends on the angle of bank. So what does the airplane wing loading depend on? It depends on the angle of bank that you're putting in the airplane. Now, for a given angle of bank, the load factor remains constant. But as you do increase the angle of bank, the stall speed increases and the load factor increases as you roll it into the bank. But for a given angle of bank, you have a given load factor. Now, if the airspeed while you're in that bank is increased at a constant bank angle, the load factor remains constant, regardless of the air density and the resultant lift vector. What would happen then if you're in a specific bank angle and you put the airplane in this bank angle and speed the airplane up, the radius of turn will increase and the rate of turn will decrease. So for a given angle of bank, the load factor remains constant, but when you change the speed of the airplane, you change the radius of turn and you change the rate of turn. Now let's take a look at an example of that. Let's assume that you have an airplane in a bank. We'll say a level 60-degree bank turn. By the way, how many G's are on an airplane in a 60-degree turn? You got it, 2 G's. And let's assume you keep this airplane in a 60-degree bank turn and you increase the speed from 90 knots to 135 knots. What's going to happen to the load factor when you increase the speed of the airplane? And the answer is the load factor will stay the same, but the radius of turn will increase. Now, most normal category airplanes are designed so that they can, well, all normal category airplanes, most small airplanes are designed so that the maximum load factor, maximum positive load factor you can put on the airplane is what? 3.8 G's. So the load factor for normal category airplanes is 3.8 G's. Now, here's a question. Let's assume that you put baggage in an airplane that weighs 90 pounds, and it's a normal category airplane. You know that's a 3.8 G airplane. And let's assume the baggage compartment is placarded that it has a maximum weight of 100 pounds. Now, let's assume you roll this airplane into a bank and get 3.5 G's on the airplane, or some other way, fly in turbulence or pull out of a dive. Somehow you get 3.5 G's on the airplane. The question is, would the total load of the baggage be excessive as far as the baggage compartment was concerned? Well, let's figure it out. First of all, total load is the load factor times the weight. And the baggage weighs 90 pounds. The total load is 3.5 G's times 90 pounds. So that baggage sitting in that baggage compartment of that airplane would feel to the airplane as if it weighed 315 pounds. Now, the baggage compartment is placarded for a maximum weight of 100 pounds. Let me ask you a question. Did you exceed the capacity of that baggage compartment? And the answer is no. Because when they built that baggage compartment, they built it to take a load of 3.8 Gs with 100 pounds in it. So that baggage compartment was actually built to take more than that 315 pounds, and that's why there is a limit on the amount of baggage you can put in a baggage compartment. So it would not be excessive. Now, what happens, let's assume you pull out of a steep dive and you do put some load factor on an airplane. Well, in a rapid recovery from a dive, the effects of load factor would increase the stall speed of the aircraft. So the stall speed would increase. If you bank the airplane for a turn, would that increase or decrease the stall speed of the airplane? Of course, banking an airplane for a turn increases the load factor and increases the stalling speed of the airplane. Now, let's take a look at Figure 4, and let's take a look at a couple questions they're going to ask you about this. First of all, they're going to give you an airplane. You don't even have to win a sweepstakes. They're just going to give you an airplane, and they're going to say that that airplane has a stalling speed of 60 knots. And they're going to have you roll that airplane into a turn such that you have a 2G load factor on the airplane. Now, what's the stalling speed of the aircraft? Well, you have to figure out where 2Gs occurs. Here's 2Gs over here. You read across here until you get the load factor line. Read right straight down. You find out 2Gs occurs at 60 degrees bank. So you start at 60 degree bank now and go up to the percent increase in stall speed line and transfer off over here and read the percent increase in stall speed, and you've got a 40% increase in stall speed. Now remember, when they gave you this airplane, they told you this airplane stalled at 60 knots. So you take that 60 knots and multiply it times 140% because you had a 40% increase in stall speed. So that's the same as multiplying it times 1.4. And now your stall speed is 84 knots. So they simply want you to know when you roll the airplane into a steep bank, put a couple Gs on the airplane, you do increase the stalling speed of the airplane. Now let's take a look at another question they're going to ask you on Figure 4. They're going to say what increase in load factor would take place if the angle of bank were increased from 60 degrees to 80 degrees. Now, 80 degrees is a steep angle of bank. Well, we can take a look at the 60-degree bank, and we find here's the load factor line. We read across to the left, and we have 2 Gs on the airplane. Put this airplane in an 80-degree bank, go up to the load factor line, read across to the left, and now, in an 80-degree bank, you have 6 Gs on the airplane. So how many Gs did your load factor increase? And the answer is you had 2 Gs, now it went to 6 Gs. You had an increase in load factor of 4 Gs. Now make sure you know what they're asking. They ask you for the increase in load factor, and it's 4 Gs, and you can see that rolling an airplane into steep banks puts a lot of load factor on the airplane. Now you've heard pilots talk about flying an airplane within the envelope. Well, here's the envelope they're talking about right here on Figure 5. And this chart is basically a graphical representation of the Federal Aviation Regulations that tell a manufacturer how strong he has to build an aircraft. Let's take a look at it and see if we can make some sense out of it. Across the bottom is the speeds of the aircraft. On the left-hand side is the load factor on the aircraft. And what we're going to find is that the normal stall speed of this airplane under 1G is about 62 or 63. But as you put load factor on the aircraft, the stalling speed of the aircraft increases like so until you get the maximum load factor the airplane's built to take, which is 3.8 Gs. You read right down from that point, and that's when the airplane stalls at 3.8 Gs, and that's 120 or 123 for this particular airplane, and that is the maneuver speed for the airplane. And that is the maximum speed at which you can make an abrupt and complete deflection of the controls without causing structural damage to the aircraft. In other words, you can be flying along at maneuver speed, reach forward, grab the wheel, and jerk it back in your lap as hard as you want, and not cause structural damage to the aircraft because the aircraft will stall before the wings become damaged. Scare the daylights out of everybody on board, but you won't cause structural damage to the aircraft. Now, if you roll this airplane upside down on its back, it's going to have an upside down stalling speed. And here is the curve right here that tells you the upside down stalling speed of the aircraft with Gs until you get the maximum speed you can safely fly the airplane, or maximum number of Gs you can safely put on the airplane upside down. And that's a negative load factor that's allowable for this airplane. So you have to fly the airplane within 3.8 Gs positive and this negative load factor, or else you might cause structural damage to the aircraft. And if you fly, for instance, at 80 knots and put 3 Gs on the airplane, what's going to happen? It's going to stall. But if you fly the airplane at 140 knots and put 3 Gs on the airplane, it'll just fly with it, no problem at all. Well, let's do another one. Let's assume you put about 4.5 Gs on the airplane at 80 knots. What's going to happen? It's on the left-hand side. It's going to stall. But if you put 4.5 Gs on this airplane over here at about 160 knots, what's going to happen? Structural damage to the aircraft. So that's what this is all about. You got to fly the airplane inside this envelope. You get over here, you're going to stall. Up here, you're going to have structural damage to the aircraft. Now, another thing you need to look at is here is a line that tells you what a 30 foot per second gust load factor does to the aircraft. If you got hit by a 30 foot per second gust load factor, we'll say at 80 knots, the airplane's going to stall. In here, it's going to fly, and here you have maximum structural cruising speed. Now, if you remember, maximum structural cruising speed is the top of the green arc and the bottom of the yellow arc on the airspeed indicator. Now, what is the significance of maximum structural cruising speed? Well, maximum structural cruising speed is the speed above which anything more than light turbulence could cause structural damage to the aircraft. And the regulations say that at maximum structural cruising speed, a 30 foot per second gust load factor can't put any more than 3.8 Gs in the airplane. In this particular airplane, it puts a little bit less on the airplane. So that's maximum structural cruising speed. Anything above maximum structural cruising speed is shown by the yellow arc on the airspeed indicator. And then you have the red line, which is never exceed speed. And then finally over here is design dive speed. Well, you're not allowed to fly any faster than never exceed speed. All right, let's take a look at the questions they're going to ask you about this on the test. First of all, they're going to say what's color-coded and what's not color-coded on your airspeed indicator. Is maneuvering speed color-coded on your airspeed indicator? And the answer is maneuvering speed is not color-coded on your airspeed indicator. And how about maximum landing gear extended speed? No, that is not color-coded on the airspeed indicator. Now, maneuvering speed is, as we said earlier, the maximum speed at which you can make a full or abrupt control movements without causing structural damage to the aircraft, but it is not shown on the airspeed indicator. It's placarded on the panel. Now, let's assume you're flying along in an airplane and you get into severe turbulence. What would you like to do? You'd like to reduce the airspeed to below maneuver speed, because if you get the airplane to maneuver speed or below, no amount of turbulence will cause structural damage to the aircraft, because the airplane will stall first. So you want to get the airplane down here so that if you hit severe turbulence, it's going to stall rather than having structural damage, which you would have over here. So if you're entering an area where you expect significant clear air turbulence, what you do is adjust the airspeed to that recommended for rough air, and in little airplanes that is maneuver speed or below. Now, once again, what's the significance of maximum structural cruising speed? Well, it's the maximum speed at which an airplane can be operated during normal maneuvers, and anything more than light turbulence could cause structural damage if you're above that speed. Now, you can never exceed speed. Never exceed speed is called VNE, and I'll find it over here. Here's never exceed speed, called V sub NE. And it should never be flown at that speed or above that speed, because design limit load factors may be exceeded if you encounter a gust, and that is the red radial line on your airspeed indicator. They're going to ask you some questions about figure 5 here on the test. They're going to say, what does the horizontal dashed line from C to E represent? Well, here's C and here's E. What's this line represent? And the answer is the positive limit load factor. 3.8 Gs is the positive limit load factor. What's the vertical line from point D to point G represent? Well, point D to point G is this line that goes right here like so, point D to point G. And that is the maximum limit of the green arc on the airspeed indicator, and that's maximum structural cruising speed right there. What's the vertical line from E to F represent? They're going to ask you on the test, and that's red line or never exceed speed, and that's E to F like so. So that line from E to F on figure 5 on an airspeed indicator represents the top of the yellow arc and red line. By the way, the bottom of the yellow arc, one more time, is maximum structural cruising speed. And once again, the most important speed to fly in turbulence, maneuver speed, is not shown on the airspeed indicator. So if you do get in severe turbulence, what you want to do is aim for maneuver speed. But the way you do it, and this is an FAA test question, is set up a power setting and a trim that you know will get your maneuver speed or slightly below, and then maintain wings level attitude and accept variations in airspeed and altitude. Because 9 times out of 10, when an airplane comes apart in turbulence, it's the pilot that tears the airplane apart, not the turbulence, because the pilot has the nose get down, starts to lose altitude, and jerks back on the wheel and tears the wings off the airplane. So set a power setting and a trim that you know will get your maneuver speed or slightly below, and then maintain wings level and accept variations of airspeed and altitude. Now, if up till now you have not believed in wingtip vortices, take a gander at this. Isn't that something? This is a Boeing 747 with smoke generators on it, demonstrating wingtip vortices. And that's the principal cause of hazardous wake turbulence behind a large aircraft, is these wingtip vortices. Boy, these can roll you on your back, and on short final, that can run your whole doggone day. So how do they work? Well, anytime an airplane is flying, you have relative high pressure underneath the wing, relative low pressure on top of the wing. It's that pressure differential that creates lift, and that's what makes an airplane fly. Well, anytime you have a high pressure area next to a low pressure area, the molecules from the high pressure area are going to try and make their way around the wingtip and slam themselves down on the wing to join the molecules in the low pressure area. The problem is, by the time these molecules make their way around the wingtip, the top of the wing is gone. It isn't there anymore, and you really get these little wake turbulence or wingtip vortices, and they're very much like tornadoes, and they can just be terrible for a little airplane flying in this. Now, this wake turbulence is greatest when the pressure differential at the wingtips is greatest. And the pressure differential at the wingtips is greatest when the angle of attack at the wingtip is greatest. So let's talk about when the angle of attack at the wingtip of the airplane will be the greatest. First of all, would it be when it's heavy or light? Well, it's when the airplane's heavy, because you have to have a bigger angle of attack when the airplane is heavy. How about when you're flying fast or slow? Well, when you're flying slow, you have a bigger angle of attack, so slow would be the case. Now, how about when the airplane is clean or dirty, that is, flaps up or flaps down? Well, when the airplane is flaps up, to get the same lift at the same speed, you have to have a bigger angle of attack at the wingtips. So wake turbulence is greatest and the vortex strength is greatest when the airplane is heavy, clean, and slow. Now, these vortices occur any time there's lift on the wings, so when an airplane rotates for takeoff, now there's lift on his wings, and these vortices begin when he rotates. Now, as the airplane climbs out, or anytime the airplane is flying, the vortices descend behind the aircraft. When they hit the ground, they diverge or move apart from each other, and they drift with the wind. So a light quartering tailwind can hold the upwind vortex right over a runway, while the downwind vortex will drift further downwind. So a light quartering tailwind can hold this vortex right over the runway, and that makes the problem with wake turbulence a lot worse. So if you're taking off behind a big aircraft, what you want to do is be airborne prior to reaching the point where the jet rotated. Then you want to climb above his flight path and then stay upwind of the jet's flight path if you can until you're able to turn clear of its wake. So try and get airborne before he does. Outclimb him if you can. If you can't, in a Cessna 150, you'll play heck out climbing a 727, but turn and go upwind. Now, let's assume you're getting ready to take off in an airport and a big jet comes in and lands in front of you like this. Well, you don't want to fly through his wake turbulence, and he has wake turbulence until his nose wheel touches the ground. And what you want to do is keep track of the point where his nose wheel touched the ground, and then you want to stay on the ground during your takeoff later until you're beyond the point where his nose wheel touches the ground, and then you won't be in his wake turbulence. Now, let's assume you're landing behind a large jet aircraft. What do you want to do? Well, remember, his vortices descend behind him. And so what you want to do is, once again, notice where his nose wheel touched the ground and land beyond the jet's touchdown point, particularly where his nose wheel has touched the ground. Now, let's assume that you're on a cross country and a big, large jet like this crosses in front of you. The FAA is going to say from left to right, approximately 1 mile ahead, and that's your altitude. What should you do to avoid wake turbulence? And the answer is you should make sure you are slightly above the jet's flight path. Now, let's assume today, instead of flying in the vicinity of a big iron airplane, holy mackerel, you're flying in the vicinity of a big iron helicopter, just like this. Well, do you have to worry about wake turbulence behind a helicopter? And the answer is yes, you do. You have vortex circulation behind a helicopter just like you do behind an airplane, and it trails behind a helicopter in forward flight just like it does with wingtip vortices generated by an airplane. Now let's take a look at one other thing very similar to wake turbulence, and that is ground effect. Anytime an airplane is flying, there is high pressure underneath the wings, low pressure on top of the wings, and some of that air is going around destroying lift on top of the wings. But when an airplane's within about a wingspan or less of the ground interferes with the ability to get around the wing and destroy some of the lift on top of the wings. So when you're in ground effect, about a wingspan or less of the ground, some of the lift that would have been destroyed is no longer being destroyed, and the airplane actually flies a little bit better in ground effect. So ground effect increases lift, reduces drag, and lowers your stalling speed. So an airplane leaving ground effect will experience an increase in induced drag and require more thrust, because when you leave ground effect, you no longer have the help that you do when you're within about a wingspan of the ground. Now, so if you keep the same angle of attack in ground effect as when out of ground effect, what's going to happen is lift will increase when you get back in ground effect for landing, and induced drag will decrease as you're coming in for landing. So to produce the same lift while out of ground effect as when in ground effect, you'd have to increase the angle of attack. And when you get back in ground effect, you'd lower the angle of attack. Well, believe it or not, you and I have covered everything the FAA wants you to know about aerodynamics, and even so, we still can't figure out what makes this thing fly.